What is going on, guys? My name is Hussein and welcome to the Backend Engineering Show. Today's topic is write amplification, database write amplification. You know, guys, this is one of the reasons that Uber have moved from Postgres to MySQL. And we obviously talked about that move that is not entirely approved by the community because Uber did miss a lot of things in that article, but it was a valid reason nevertheless. So write amplification, if you don't know, guys, it's like a phenomena where your update statement or your SQL or whatever write you're performing logically, the actual physical representation of that write is double or not triple or maybe a magnitude more, order of magnitude more than the actual logical write. So you would think like, hey, I just updated a single field in a single row, but you look at the disk usage at that point and you see it doing thousands and thousands and thousands of kilobytes. Like what I merely updated a 32-bit integer. What the heck happened? The write amplification, you can look at it from 3 tiers. The first thing, which I saw from building apps, right? And I call it the application write amplification. The second type is the database write amplification. And the third type is the disk write amplification, which is the SSD write amplification. I'm going to talk about the 3 of them. You're gonna have you can see jump codes on YouTube, and I'm gonna put the same jump codes in the podcast where you can jump into the interesting part of thing. SSDs are infamous for write amplification, so I'm gonna talk about that. And then database, which is something that is hidden from you. It depends really database platform. And then the application itself, which is kind of your fault as a backend engineer. So let's jump into each one of them. All right, so let's start with the application write amplification. And this is maybe your end user is expecting something, right? But it turns out that the actual work behind that API single call or update is magnificently larger. For example, you're ticking your to-do item. Hey, I just done this task. But so to the developer, the front-end developer in this case, calling that API to kind of just, hey, I just deleted. I just marked this as done, right? So front-end developer might think, oh, this is just an update statement, maybe on a single row. But a back-end developer could have written this application in a way so that, hey, it goes to the to-do app, mark that to-do as done, and then goes to another table, maybe inserts that row into another archive table. Hey, the Hussein has washed the dishes, for example. It goes into another, so that's 2 writes. And then maybe you have another table maintaining the count of the task that you've done. So your increment or your update another table with the actual work. So one single API translates to many writes, and obviously this goes downstream and affects that thing. So this is the simplest part of thing. You think it's a single write, but at the actual API implementation, it does a lot of things. And relational databases are designed this way, especially if you have normalized table where you have many tables that you have to kind of maintain and keep it consistent, right? That doesn't mean obviously NoSQL is infamous of that. Obviously it has its own limitation as well. But now this is the first type, the application write amplification. Your app claims to do one thing, but actually behind the scene is doing way more. Another famous thing is delete. Some people implement deletes as an actual update and an insert. Some people implement deletes as a logical delete, right? Where they do more work at the back end. So it really depends. So that's application write amplification. Let's talk about database write amplification. And this is, whenever you hear write amplification, it could be either the database write amplification or the other one, which is the SSD write amplification. So the database write amplification is a property that is hidden from you as a database platform. I'm going to give the example of Proxies because it's the most infamous, and it is the exact same thing as MySQL, but with a MyISIM storage engine. right? They both work almost identically in this case, almost, not quite. So let's say you have a table with 6 columns, right? 5 columns have an indexes, each has an index on them, and the last column, which is the 6th column, doesn't have an index. So if you execute an update statement, you pulled a single row on this table, and then you updated one of the columns, let's say column 1, which happened to have an index on them in Postgres, this is what will happen. Postgres will create a brand new row. That's how it works. Always, any update, any modification on the tuple always create a new tuple ID. There is a tuple ID that uniquely identifies the rows. Yeah, it will create a new one with the new values that you have. A copy, exact copy. We have to update its corresponding index because we changed the value. So now we update the index. That's something we have to do anyway, right? So that's another write. So we inserted a new row, and now we want to go to the index and change that tuple ID from pointing to the old row, it points to the new row, and we also change the value. We introduce the new value that you inserted in that tuple in that, right? So now it's almost 2 changes, right? You might say, Hussein, what about the rest of the indexes? These 5 indexes still point to the old row. Postgres used to update those indexes to point to the new tuple. And that's what Uber didn't like back in what, 9.1 or 9.2? I don't remember. And so the write volume that is happening as a result was enormous, right? Especially when you start, you did a single update, now you're touching all these indexes, and if you have a lot of indexes, all of a sudden these indexes have to be touched despite them not being changed. If you think about it, they were not changed, but Postgres actually solved this problem. I don't remember when, maybe it was 9.4 or 9.3, by introducing something called the heap only tuple, the hot tuple. That essentially, it's a trick. So that, okay, since we didn't really change the value, if we didn't really change a value, we don't really go to the index to update it, because that's just wasteful, right? So they definitely fixed that. The heap only tuple will create the row, the new row, the tuple ID, and then points the old row to the new one. They say, hey, by the way, if anyone happened to land on the old row, tell them that there is a new version of this. There is a new heap only tuple that points. The only limitation here is it has to be in the same page, right? If the page is full, then you cannot really do that, right? That's why it's called heap only. That's why will fill factor come in. You have to choose the correct fill factors. It's a really complex things to understand. You have to be really careful when you're building this stuff. Anyway, so it used to do that, but no anymore. But I wanted to give this example. So write amplification is a thing, especially with Postgres, but it could be with any other database. Let's say you did one single update. You updated one row with many values. You changed almost all columns, right? There's no way in MySQL, on Postgres, on Oracle, we wrote one single value, one single row, but as a result, we have to touch all the indexes. That's another write amplification, okay? Because if you look at the update statement, logically, it looks to me like updated a single row, but to the database, you actually did more and more work. You did a lot of physical work, right? And when I say physical here, I mean database physical, right? Because it gets really confusing when I say logical and physical. Where are you really? When I say logical database write is the SQL, and physical database writes are essentially the wall changes, the write ahead logs, right? All these actual changes that you have, the pages, right? But when it comes to the SSD, which is the next topic, that's a different beast, right? Physical and logical becomes different things. All right, now this is the database write amplification, very powerful. You have to really understand it, right? So that's the second type of amplification. Now that goes to the final one, which is a very infamous one with the write amplification. And even if you go to the wiki page, when you write write amplification, that's the only one that shows up anyway, which is the SSD write amplification. So to talk about that, we really need to understand how SSD really works, right? So SSD guys have this idea of, someone invented something called the charge trap. Is a technique where you can store multiple level of electrons, right? You can from 0 electrons up to the certain levels, and the quantity of the electrons determine certain values, and this is the trick we use to correspond to this. And these charge traps are put into cells, like so a cell can have a lot of charge traps, and as a result one single cell can have up to the recent newer stuff up to 16 different charge levels. So if you do the math, right, with the computer science, 16 is how many bits? It's 4 bits, right? So that means each cell can store 4 bits. And once you charge them, you store them, you can turn off electricity. Works. It's persistent. It stays for ages. It does not go, it does not get released, right? And you can essentially read those values back, and then based on the quantity of number of electrons, you say, okay, this is 0000. Oh, this is 0001. Oh, this is 0010. This is 1111. Based on this trick, they build the entire SSD. So now they took one cell, they organize it into a row, and then the rows becomes the pages, right? So there is a page has many cells and many rows, right? So think of a page now. This have a lot of these charge traps. So a page can have a lot of bits stored in it, and you can do that. And then pages are organized into blocks, right? And here's the trick here, right? So now you have control of a block that has many pages, and this is what we're interested in here at this level, right? If you love to read more about it, I'm going to reference a video that I absolutely love. It's a very technical, low-level thing if you're going to learn more about SSD. It's very good animations too. I loved it. So now this is what we need to understand: block and pages. However, nothing is free, obviously. Here's the condition with SSDs. Yeah, you can write stuff for us. You can write in pages, right? As long as the page is empty. It doesn't have anything, right? It doesn't have any levels, okay? As long as the page is empty, you can write anything you want in it, right? And when you write it, we're gonna store it. But if there is a page that is already has some content in it, and you wanna update that content to something else, let's say you have a bunch of rows and have values, you want to update something, you have to erase this page and write it back. You cannot just overwrite it, right? That's impossible. So what the SSD does when you want to update, so what it does is says, okay, let's just write the new value into a brand new page and then leave the old page as a stale, mark it as stale. So future people can clean it up if they want to use it, future requests, right? And here's another limitation in the SSD. You cannot clean up one page at a time. You have to clean a whole block. And here's, you can see some pictures here of a block. A block has many pages, right? And a page, I think it's 8K or something like that. If I come with a payload, I want to update a page, right? I have a block with 3 pages. I have 4 pages. Let's write them A, B, C, D. We just write them back right there. Okay, and then let's follow that. You can see the second picture. I took this from Wikipedia resources, right? And then let's follow it up with writing E, F, G, H, right? And then so that's 4 pages. But I also want to update pages A, B, C, D. So an update, what does it do? It marks those old A, B, C, D pages as stale, and then writes new 4 pages in the same block. So now this block is filled. If you have new writes that you want to come in and you want to use this block, you cannot use it. To the SSD drivers, this is filled. This block is filled. You cannot use it at all, right? And as a result, it's just filled. You cannot use that block. So there's this process that's called garbage collection, right? And it runs asynchronously. It cleans up this kind of thing. So this block has 4 pages that is in use, and it's costing us a lot of precious page memory space, right? So what we do is, hey, garbage collection, move all the active pages from this block into a brand new block, and then just slam that block shut, clean, flush the whole thing, clean it up, so I can use it and I can start using all the free spaces. So now my pages have moved to the block, the second block, and I have now around 4 spaces that I can use to write this stuff, right? That's why SSDs do not like updates because of this thing, right? You're marking this pressure old pages as stale and then writing in the new locations every time, as opposed of new, fresh, nice sequential writes, right? Every time you're just using new pages, you're never touching the old pages. So if you don't touch old pages, if you don't touch old data, you're never gonna mark these pages as stale, and you're never gonna have blocks with stale pages, which is the worst thing you can do. If you have blocks with stale pages that have been updated, the garbage collection is gonna kick in, and the wear leveling, another thing that's gonna kick in, which is going to start flushing and moving new pages to new blocks, and then flushing blocks. All this work, all the SSD is going to do as a side effect of your original write, right? So updates are the worst thing you can do to SSDs, right? Like SSDs always like beautiful, just single writes, right? That's why BTrees, right? If you go to the databases, BTrees causes this kind of behavior over time on SSDs, because even if you're doing only inserts, BTrees still need to get updated. You're updating in place a B-tree pointer. You're updating in place B-trees locations. You're rebalancing the trees. And when you do that, B or BP plus 3, when you do an update, what do you do with SSD? You go to that page where it exists, slam it as stale, and then take that value, take the new value and write it to a new block. So now, the more you do this, the more you're going to have blocks with stale data. And when you have blocks with stale data, garbage collection will gonna kick in. This can start moving your precious block to some place, which is an expensive process. If it's gonna happen again and again and again, eventually your SSD will gonna wear down very, very quickly. Right, because you're gonna start using all your pages unnecessarily. Let's put it this way, right? And when you start using all the pages in SSDs have this algorithm with wear leveling, where they essentially says, okay, I have this page sitting for years, nobody touched this, and nobody written in that page, and maybe I forgot to mention that, but the page has only limited amount of time to write, after which it just dies. That page location just dies. You cannot write to it after maybe 2,500 times or whatever. There is always, the SSD has a lifetime, right? So there will be, without wear leveling, there will be pages that is very busy, where you are writing to it a lot, this physical location, right? And there will be pages that are never touched, so they will be unbalanced. So wear leveling is an SSD concept where it actually balances this thing. It says, okay, hey, this is a cold page from 1998, nobody touched it. Let me move it to a new location, and let me use that precious location to write new pages, because you're doing all these updates, right? Eventually, all right. So as the more you're doing that, the more wear leveling gonna kick in, and it's gonna start using all these pages, all your SSDs in a balanced manner, right? So updates always kills your SSD faster, essentially. When I say that, I'm talking years and years. Obviously, I'm not talking about months here, right? So yeah, that's why people came in with log structure merge tree as an append only, so that we are having nice inserts tucked in together, so my blocks don't have these stale pages. It always have a consecutive pages that are never updated, and as a result, SSDs love this stuff. You're gonna have pages that are never updated. As a result, they're clean, right? If you go back to old pages and start updating them, SSD have to move them to a new location. They have this block now all of a sudden have a stale page, and all of the other pages are used, so it has to move those pages to somewhere else and flush it and reuse it, and that's a lot of work for the SSD. All right, guys, so that was the right amplification from the application point of view, from the database point of view, and from the SSD. So your single to-do, marking the to-do app as done, if you're doing that single update that the front-end developer thinks that you're doing a single update, but you're actually touching all these tables, and those tables kick in the database write amplification, which, hey, each table has like, 7 indexes, and this table have 3 indexes, and this table have, 4 indexes. Those, if you're touching those, obviously, values with indexes, then those corresponding indexes have to be touched. And here's another one, right? In Postgres, there's this concept of toast tables, where a string, if there's a long string, it never stored in line, right? It's stored in another table. That's a toast table. So that table needs to be updated. So the write amplification just triples, if you need double, just like order of magnitude. It's a lot of work. And then now all these writes, which some of them are updates, some of them are inserts, it translates to SSD write amplification at the physical disk level, right? So all these pages that you have to update and then move the new page, right? Mark the old page as stale, move the create a new page, and then have the SSD point the logical page pointer to the new page, physical page, because that's another thing. The physical and the logical is an SSD concept. I know, guys, it's a very complex topic, but I just wanted to make a video raw like that. It's a very, very important topic to understand, and we're gonna have to make a new and more videos about this, and maybe I'm gonna make a practical video discussing this in details. All right, guys, I'm gonna see you in the next one. This has been the Backend Engineering Show. This was a write amplification. Just keep an eye on it. It's really critical. Goodbye.